Hello everyone. In this lecture, we are going to draw the Root-Locus sketch for a system given with the following transfer function. So GP of S is equal to 6 over S times 1 plus 2 times S. And GC of S is given in the form of a proportional controller. So GC is equal to KP. As usual, the first step is to write down L of S, which is GC times GP, and it will be equal to 6 times KP over S times 1 plus 2 times S. And we can rewrite it in order to make it, let's say, more proper for drawing the Root-Locus. I can take 2 out, so we will have 2 times S times 1 plus 1 over 2. Or we can rewrite this as 3 times KP times 1 over, this is S, so S plus 0.5. And we can rewrite it as rho times 1 over S plus 0.5. So this could be considered as our loop transfer function. And we know that rho is equal to 3 times KP. Okay, so we should keep this in mind. N of S for this example is equal to 1, and D of S is equal to S plus 0.5. Therefore, we can say that N is equal to, I just missed S over here. So we have S times S plus 0.5. And as a result, D of S is also equal S times S plus 0.5. And therefore, N will be equal to 2. Okay. So N is equal to 2. M is equal to 0 because we have no zeros for this system, and therefore R, which is equal to N minus M, will be equal to 2. And this will tell us that there are 2 asymptotes. There are 2 asymptotes for our system. We need to find out XA and KCA for our asymptotes in order to be able to draw them. Let's start by drawing an empty S-plane. One for positive locus and one for negative locus. So we have the real axis and imaginary axis here and there. Our system has no zeros and we have 2 poles. For the open loop system, S times S plus 0.5 equal to 0 will give us the open loop poles of the system. S1 is at the origin and S2 is at minus 0.5. We start to locate them at minus 0.5 and at the origin, at minus 0.5 and at the origin. We know that our branches will originate from the poles and they will move towards infinity because there are no finite zeros for our system in this case. Now we can find out the value for XA. Sum of Zi's minus sum of Pi's over N minus M. N minus M is equal to 2. For sum of zeros, we have 0. Minus, for the Pi's, we have one is 0, the other one is 0.5. So therefore, we will have minus 0.25 as the point of abscissa. So XA is equal to 0.25. For KCA, R times KCA will be equal to 2h plus 1 times pi, and 2h pi for the positive locus and negative locus. And since we have two asymptotes in this case, h will be equal to 0 and 1. And r is equal to 2. So Kc A will be equal to, if I replace h with 0, we'll have pi over 2. If I set h equal to 1, we'll have 3 pi over 2 for the positive locus. And for negative locus, we'll have 0 and pi. Now that we have this information, we can start to draw the asymptotes. Okay, let me see which color is proper to draw the asymptotes. Let's use the blue color. This is the point of abscissa, minus 0.25. For the positive locus, we have pi over 2 and 3 pi over 2. So pi over 2 will give us this asymptote, and 3 pi over 2 will give us this asymptote. These are two asymptotes. For the negative locus, point of abscissa is the same place. In terms of the angle of the asymptote, we have 0 and pi. So one asymptote will be like this, and the other asymptote will be like this. Okay, so we are done with the asymptotes. Now we can check the parts of the real axis that belong to Root-Locus. Okay, so segments of the real axis. We can divide our real axis into three segments, from minus infinity till minus 0.5, from minus 0.5 till 0, and from 0 till plus infinity. In each case, we can count the number of the poles and zeros. I just draw the system again here. So we have 1 0 here, 1 pole over there, 1 pole over there, minus 0.5. And now if we count the number of the poles and zeros to the right side of this highlighted area, we see that there are two poles in it. If I check the number of poles and zeros to the right side of this highlighted area, we will get only one pole. And finally, if I count the number of the poles and zeros to the right side of the third highlighted area, we will get 0. Therefore, we can say that the area from minus 0.5 till 0 belongs to our positive locus, and the other two belong to our negative locus. Okay, so this part of the real axis belongs to our positive locus, and these parts of the real axis belong to our negative locus. And we know that our branches will originate from the poles. So I think you can see it over there, yeah? We will have one branch originating from the pole at the origin, and then it will move on the real axis. The other one will originate from the pole at the origin at the pole at minus 0.5. It will move towards the pole at towards the branch, the other branch indeed. At some point they will meet, and then they will depart the real axis. So we need to find out a breakaway point over here. Breakaway point is needed. We should find out the exact location for that. On the other hand, for the negative locus, if we check the branches, one will start from the pole at the origin. It will move on the real axis towards the plus infinity using this asymptote that we already have drawn, and the other one will originate from the pole at minus 0.5 and move on the real axis towards minus infinity. So we can see that there is no breakaway or break-in point for the negative locus. Okay, now let's figure out where is our breakaway point. If you remember, in order to find out the break-in or breakaway points, we need to refer to n prime d minus n d prime equal to s formula. For n of s, we had 1, therefore n prime will be equal to 0. For d, we had s times s plus 0.5, or s squared plus 0.5s, and therefore d prime will be equal to 2 times s plus 0.5. If we plug these values into what we have there, we will have 0 times d of s minus 1 times 2s plus 0.5 equal to 0. Therefore, we will have 2s plus 0.5 equal to 0, and out of this we will get s equal to minus 0.25. So we see that the breakaway point is equal to minus 0.25. This belongs to the positive locus because that segment of the real axis belongs to the positive locus, and it will be a breakaway point because we already had discussed it, yeah? So the breakaway point will be this point. It's both XA and a breakaway point. So at that breakaway point, we will have two branches going out of the real axis. One will go towards infinity using this asymptote, and the other one will go towards infinity using this asymptote. So this will be our positive locus indeed. We kind of are done with drawing the root locus. We don't have any break-in point. You can find out the angles of departure from the poles. You will see that angle of departure here will be equal to 0. Over here, alpha departure will be equal to pi. Here, alpha departure will be equal to pi, and over here it will be equal to 0 degrees. Okay. So, but you can find that out quite easily, even though we don't need that value over here, yeah, because we already know that the branch will be on the real axis. So the angles are kind of intuitive to find out. So this is the root locus drawing for the positive locus and negative locus. Now let's go through the points that we have here. We need to compute, if possible, the value of Kp such that the step response of the closed loop system is critically damped. We want to have our system to behave like a critically damped system. And you should remember that in the case of critically damped systems, for critically damped systems, we have two poles at the same place. If this is our S-plane, we will have two poles here and there. And then if you look at the root locus plots that we have, we see that it is not possible with the negative locus, so we can't have it over here. But with the positive locus, it is possible. So if we manage to have both of the closed loop poles right here at minus 0.25, then we will have a critically damped system. Now the remaining part is to find out the value of the rho and consequently the value of Kp. You should know that we can do it by applying the amplitude condition. Amplitude of n over d will be equal to amplitude of minus 1 over rho. For n we have 1, so 1 over, for d we have, you can either plug the value of s into the expression for D, we know that D of S is equal to S times S plus 0.5. If I replace S with minus 0.25, we will have minus 0.25 times minus 0.25 plus 0.5, and this will give us 0.25 squared. So 1 over 0.25 squared is equal to minus 1 over rho in terms of amplitude, and therefore rho will be equal to, and since we are dealing with the positive locus, rho will be equal to 0.25 squared. And again, keep in mind that rho has a positive value. On the other hand, rho was equal to 3 times Kp. Okay? Since rho is equal to 3 times Kp, we can figure out the value for Kp. Kp will be equal to 0.25 squared over 3. And we will have the value for Kp. In the next point, we need to find out the steady state error to R of t equal to 5 times ramp of t for the same closed loop system with the obtained Kp or rho. So rho is equal to 0.25 squared. L of S is equal to rho n over d. So we have 0.25 squared times 1 over S times S plus 0.5. This is L of S that we have for our case. Now we want to find out steady state error for ramp input. We need to find out Kv first. So Kv will be equal to limit of S times L of S as S goes towards infinity, and this will give us S goes to 0, S times L of S as S goes towards 0, and this will give us 0.25 squared over 0.5. And we will get 0.25 over 2, which will be equal to 0.125. So we have value for Kv. In order to obtain the steady state error for the unit ramp, we have it in the form of 1 over Kv. But since here we have 5 times ramp, we will have 1 times 5 over the value of Kv. So we will have 5 over 0.125. This will be our steady state error. And the last point is that asking about finding the range of values of Kp such that the closed loop system is bibo stable. For this, we can have a look at the Root-Locus plots that we just created. If you look at positive locus, you can see that for all values of Kp bigger than 0, our system is bibo stable, because both poles are on the left half plane. On the other hand, for the negative locus, you can see that for any value of Kp or rho is smaller than 0, we have one pole on the right half plane. So the system is not bibo stable. And if we want to conclude, we can say that for any value of Kp or rho, for rho bigger than 0, which means that for Kp bigger than 0, we have our system as a bibo stable system. We can also compare the Root-Locus plots that we have obtained with MATLAB. Over here I already have drawn. So you see that this is what we have for positive locus and for negative locus. For the positive locus, we have one branch like this, and the other branch is this one. it's basically the same as what we have drawn. And for the negative locus as well, we have obtained the same result as the one that is achieved by using MATLAB. Alright, so that's it for this example. Thank you for watching and see you in the next example.